Presently we are going through our topic of tries under the series Advanced Data Structures and Algorithms, and let me give you a quick recap of what we have done till now in this topic. So we have started with tries, we understood what actually it is, and we have seen how this try is actually going to be formed in our kind of initial lectures. Then we started with some basic operations like insertion, search and deletion, and we also looked into the two very prominent applications. One is word matching, another one is prefix matching. Then we have particularly seen two kind of stages or two versions of deletion. One is in which we want to delete a word which is a part of another word, and the second one was we want to delete a word which is not part of any other word. So till this point we have completed in previous lectures. Now let us start with a kind of a different version of tries, which is known as compressed try. So compressed try is actually a try which is having nodes of degree at least 2. Now what do I mean by nodes of degree at least 2? I am explaining in a short while. This compressed try is actually obtained by standard tries only, and these standard tries are in this standard tries the chains of redundant nodes are actually compressed. So what do I mean by this compressed try? In order to understand this data structure compressed try, we need to see one standard try example. So we will be taking the example which we have initially seen, which in which the string set S was comprising of 8 strings, that beer, then bell, bid, bull and so on and so forth. So here is that standard try which I am talking about. It is having a root node, and from the root node there are going two branches. One is going towards B, another one is going towards S, because this B is actually the two branches are there because the strings which are being kind of which are part of this string set S are either beginning by with B or beginning with S. So with beer we have the string when which is beer, then we have bell, then we have bid, then we have bull and then we have buy. Now see what is happening in this particular try, that if you can see the string beer. So B and E are actually common parts between beer and bell, and after that if we follow the branch of beer, A and R are basically the nodes which are not part of any other words. Similarly, when I am talking about bell, this last two letters which are L and L are not part of any other word, that means they are not common. Similarly, if I am talking about I and D in bid, those the two letters are also not part of any other word. So can these be kind of compressed, or these chains can be reduced in the sense, can I put this A and R of beer in one particular node? That is going to give me a save that is going to save one particular we can say link here. Or in case of bell, can we put the last two letters which are L and L in one particular node? Then in case of bid, I and D can be again kind of put into one particular node, and in case of others, for example bull, so same L and L can be kind of put into one particular node, and this is going to save one link here. So that is what we call compressed try, and this compressed try will be kind of will look like this as the try which you are watching on the screen. So we have a root node, then B, then E, A and R are combined, then B and E, LL are combined, in bid I and D are combined, in bull again L and L are combined, and in buy we do not have anything apart from this buy, which is uncommon, apart from this Y, which is not the part of any other word. So, we cannot compress it anymore. While if you can see the word cell, this is giving us a more advantage, in which ELL, all the three kind of letters are combined in one. So, here is this is kind of reducing not the single link, but the chain of the links in case of ELL. In case of stock, so S, T and O, T and O are again combined. In the previous non-compressed standard trie, if you can see, this T and O are different nodes, but here this T and O can be combined, and then C and K apart from stock can be combined, and then P is we do not left with any choice. So, this is basically a compressed trie, if you can see here. And in case of cell, this is giving us kind of, this is saving us a particular not only a single link, but but a chain of links, because E then L and L. So, this is a chain of links which is being saved. Similarly, stock is also giving us kind of, we can say, saving of a space, and other links also are now, this is what actually this is what I explained the concept of compressed trie with the help of a figure. Now, if we have kind of compacted, or if we have when we are talking about compressed trie, we have compressed the structure, we have compressed the loc. So, this what what efficiency it is going us to provide, it is it will be providing us in case of a space that we need to see. So, compact representation of this trie will help us in representation of an array of strings, which stores the node ranges of indices instead of substring. So, I will be showing you this compact representation in a on the very next screen. So, this is actually storing the node ranges of indices instead of string. How, that I will explain in a short while, and it uses order of S space, where S is the number of strings in an array, and the usage of this is, it serves as an auxiliary index structure for any of the what we can say in any of the databases. So, here we will be looking into the compressed representation or the compact representation of this compressed trie. So, here all those 8 strings are numbered from S0 to S9. All those strings are compressed here, which is C, beer, cell, stock, bull, buy, bid, bell and stop, all are there. And if you can say, and we have also used one more string here, which is here. So, and we have numbered each and every, or we have given indexes to each and every character. So, in S of 0, this C is SEE at the position 0, 1, 2. In S of 1, this is beer at the position BEAR at the position 0, 1, 2, 3, and so on and so forth. So, that structure, I am sure this is kind of a self-explanatory structure which is given on the screen. Now, how this will be stored as a compact representation. So, if you can see the leftmost node from the root is 1, 0, 0. So, 1, 0, 0 is actually meaning, so 1, 0, 0 means B. So, that means S of 1 is beer, starting from 0 ending at 0. So, that is nothing but the character B. Then to the left of this 1, 0, 0, we have 1, 1, 1. So, the first one says S of 1, then the second one says starting at 1 in S of 1, ending at S, ending at 1 in S of 1, which is nothing but E. So now I am not storing the characters, I am just storing the indices of the ranges. Why I am saying ranges? These two examples 100 and 111 are holding only one single letter, which is B and E. Now if we come to the leaf node, this is giving us 1, 2, 3. So that means S of 1, which is beer, starting from 2, which is A, ending at 3, which is R. So that means both the characters A and R. So B is stored in the form of 100, E is stored in the form of 111, and E and R are stored in the form of 1, 2, 3. So if you can see the second, let us take some more examples of this compact representation. Let us take 100 B, I explained, 111, that is E, and to the right of 111 we have 6, 2, 3. So 6, if we can see what is S of 6, S of 6 is actually bit. So we are talking about that string, or if we can see even the middle branch which is following 100 is 612. So 6 is S of 6, then 1 and 2 is your bid. So beer and then bell. So for bell we have S of 8 starting from 2 ending to 3. So S of 8 is bell, then starting from 2, which is L, ending at 3, again it is an L. So 6, 8, 2, 3, then 100 is followed by 612. Let us take one more example which is on the right of 4, which is on the right of 100, that is 411. So S of 4 starting letter 1, ending letter 1. So what is that? That is nothing but U. So we have seen B in the form of 100, and now this is U in the form of 411, and then 423. So S of 4 starting from 2, which is L, ending at 3, which is L. So that will be bull, LL. So B, then U for 411, and then LL in 423. Then B as 100, U as 411, and then 522. So S of 5 is by, and second character is 2, starting from 2 ending to 2, that means only a single character, which is Y. So here you can see that a compact representation of that compressed trie, not only the standard trie, but the compressed trie is again represented in, or is again provided, and representation which is very compact, and it is only going to use order of S space, where S is the number of strings in this array, and this can serve as an auxiliary index structure with saving a lot of space, and that is why we call this tries kind of space efficient data structures. So with the standard tries we can go on saving the space with the help of compressed tries. Those compressed tries are even kind of inserted, those compressed tries can even represented in the form of can be given a very compact representation. Now looking at these representations of compressed trie, or looking at this compact representation of the compressed trie, let us proceed with the basic operation of insertion in a compressed trie. So how are we going to insert a particular string or a particular keyword if we want to do that too in a compressed trie. So for example, I want to insert BB AAB B. So that is a word which I want to insert in the compressed trie, which is already existing, and it is shown in the figure which is available on the screen. So here we have a compressed trie. So if we look for as you all are aware that we need to perform the search first, even if we want to insert a particular keyword. So, insertion in a compressed trie, here we will start from the root node, follow the path B, then again we follow the path B, and then we follow the path which is only path A. Now, our search will stop here, but the tricky condition here is we are not looking for this triple A, we are not looking for 3 continuous occurrences of A. We are actually only looking for the 2 occurrences of A, and then maybe we will be kind of able to insert the 2 occurrences of B, which will complete our insertion. But in this situation we need to make a branch here. This A will go into kind of one branch, and this AABB will be one branch, and the single A which will be left after taking out the 2 A's from this BBAAA will be left out as one particular branch. So, what I am trying to say here is actually shown in this figure. So, we have followed BB, then AAA. So, this AAA, the 3 occurrences of A are actually we can say broken into 2 and 1. So, 1 will be given as the branch, because from the 2 occurrences of AA we need to pull out one more branch which will result in BB. So, our string which is BB AABB will be inserted in this way. So, what I am trying to establish here with the help of this example is insertion in actually compressed trie is kind of possible, or it is very we can say it is not very tricky, it can be performed very easily. So, here till this point we have seen what is the compressed trie. Now, coming to the next scenario, which is suffix trie. So, suffix tries we can say that is kind of a different version of this trie. So, earlier we have seen standard trie, then we have seen the compressed trie. Now, we are coming on to the suffix trie. So, suffix trie is basically, as the name indicates, the name is suffix. So, suffix trie of a string X is actually a compressed trie, it is not the standard trie, it is a compressed trie of all the suffixes of S. So, we will be taking this with the help of an example, and we are taking one particular string which is minimized, and we have seen we have kind of stored it in the form of an array. This is an 8 character array starting from 0 to 7, and if you can see the suffix trie corresponding to this string X. So, all the possible suffixes, now let us try to figure out all the possible suffixes of this suffix trie. So, one suffix could be E, another one could be ZE, then it is IZE, then we have MIZE, IMIZE, NIMIZE, and so on and so forth. So, you name a suffix or you figure out a suffix here, and you will find it in the trie. So, the first character is going to E, that is the E suffix E only alone. Then we have I. Now, this I is actually giving rise to IN, IM, then IZE is also there, then MIZE is also there. So, basically there are 3 suffixes which are starting from I. One is IZE, another one is IMIZE, and the third one is starting from 1 ending at 7. So, all these suffixes which are starting from I are arranged here in the form of a compressed trie. The first branch goes to MIZE, the second branch from I is going to NIMIZE, and the third branch, which will be totally as IZE, is going to ZE. Now, coming to the next one, which is MIZE. So, MI is kind of we can say common in MIZE, and MI is also common in MI Ni, Mi, Ze. So, Mi is also the first, the common letters in the complete string minimize. So, Mi, the branch is going to Ze, and one branch is going to Ni, Mi, Ze. Then the last branch in this suffix trie is going to Ze, and the second last branch is going to Ni, Mi, Ze. So, you again I am repeating that you name a suffix or you pick out a suffix and you will find that suffix in this compressed trie. So, this compressed trie is actually a suffix trie of a string x, which is basically I can say a trie of all the suffixes of x. Now, this compressed trie can be stored in a space order S, where S is nothing but the number of number of strings in the set S, and it is going to use order 1 space index ranges at the nodes. So, here again we have kind of S of 0, S of 1, S2, S3 until S9 we have all those strings which we have seen earlier. So, compressed trie we all are aware, and we have seen this example earlier also, that can be stored in an space order S, and this compressed trie, and now we are combining the representation of or now we are kind of overlapping the representation of compressed trie with our suffix trie. So, that suffix trie can also be kind of implemented with the help of compact representation of compressed trie, and this we have already this kind of representation we have already seen in the earlier examples of compressed trie. Now, going into details of suffix trie. So, this suffix trie which we have seen for a text x of size n, and when this is derived from an size alphabet of size d. So, when I am talking about alphabet of size d, that means for example, if we are having English alphabet, the size d will be equals to 26. This suffix trie for a text x will store all n into n minus 1 by 2 suffixes of x in order n space. So, that in a way it is an space efficient data structure. This also supports arbitrary pattern matching and prefix matching queries in order dm time, where m is the length of the pattern, and this can be constructed in order dn time. So, here if you can see in the figure, we have taken that string minimize, and we have given a compact representation as we did for compressed tries. So, the first branch starts from 7 goes to ends at 7, that means this is the branch corresponding to the character E, and then the last branch is it is ending at 7 starting from 4, which is MIZE, or starting from 6, which is just Z and E. So, this kind of compact representation can also be we can say given when we talk about the suffix tries. So, here what we have seen till this point is we have started with a compressed version of trie, then we have gone into how this compressed version of trie can be represented in a more compact manner. Then we try to understood what actually a suffix trie is, and then how the concept of suffix trie and the compact representation of a compressed trie can be kind of combined in order to have the advantages of two. Now, if we look into the kind of practical problems or the application scenarios in which these tries can be used apart from these word matching or longest prefix matching, these tries are having a very useful place or a prominent place of their own in the construction or in the working of web search engine, because the index of a search engine, which is nothing but the collection of all searchable words, is stored in a compressed trie, where leaf of the trie is associated with a word and has a list of pages URLs containing that word. So, we have a particular kind of a branch that whole branch is giving us a keyword and the associated URLs which are having that keyword is known as occurrence list, and that occurrence list is attached to that particular leaf, and this trie can be kept in internal memory, and the occurrence list can be kept in external memory and can be ranked by the relevance. So, for example, if there are Boolean queries for the set of words, for example, Java and coffee, which is Java and coffee both corresponds to the set operation intersection. Obviously, when I am talking about and, it is intersection on the occurrence list. So, the occurrence list can be kept into the external memory, can be ranked by the relevance, and the trie which is having its own leaves associated with the keywords which are kind of searchable words can be kept in internal memory. Also, with this kind of an application, additional information retrieval techniques can be used. So, for example, we can have some stop word elimination, or we can have stamming, which is to identify add, along with that to identify adding or to identify edit, and some link analysis can also be kind of we can say done. Another major or another very useful application of trie is in internet routers. So, computers on the internet, which are basically we call them as hosts, are identified by a unique address which is nothing but internet protocol, and this is usually written in a dotted quad decimal notation, and computers on the internet are identified by this kind of IP address. For example, the brown.edu or iit.ac.in is having some quad structure separated by decimals, and NSLOOKUP command on Unix is used to find out IP addresses, and an organization uses a subset of IP addresses with the same prefix. Now, when we say that same prefix, that means we are looking for something which is common, and same prefix if we talk about, that means here in this scenario your kind of tries can be used, or we can say routers can use tries on the alphabet 0 and 1 to do this prefix matching, and this can easily be accomplished as an application of tries. So, here in this lecture we started with the idea of compressed tries. We seen their kind of compact representation. Then we looked into the suffix tries, looked into the merger of kind of a combination of both the concepts, suffix tries and their compact representation, and we have seen two application scenarios. One is about internet routers and another one is web search engine, that how these trie is actually implemented or is actually used in your kind of routers or in your web search engines. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed the lecture. Thank you for a patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.